Okay, so shells aren't just always better than disk method. Obviously, the examples I've shown you, we've been using the shell method because that's what this section's about. But I want to reiterate one of the main differences between shell and disk. In the disk method, you always rotate it about the same axis as the variables. So here, this doesn't work for the disk method. We need things in terms of x if we're rotating it about the x-axis. We need things in terms of y if we're rotating about the y-axis. That was the disk method 2.2. Whereas the shell method, we can rotate about the y-axis and have things in terms of x. Well, in this video, we're rotating things about the x-axis for the shell method. What do you think things are going to be in terms of? All right. So we have a very similar definition to the rule for the shell method with the x-axis as we did for the y-axis. This time, I'm just going to draw a picture. Let's say we're looking at this region. Let's use colors. Say this is some D value up here, some C value up here, and this is our region R, and we're rotating it about the x-axis. Well, let's call this some function g of y. Again, if this were the disk method, we'd need it in terms of x, but it's the shell method, so we're going to talk about it. G of y. Okay, then I think I have all the information. Then the volume is just going to be 2 pi integral from c to d of y times g of y. That's it. It's the same formula, just with y's. So if it's about the x-axis, we put it in terms of y for the shell method. Disk method, they're always matching. Shell method, they're always opposite. And again, you could derive these methods if you remember the pictures. Disk method is a bunch of circles. Shell method is a bunch of cylinders, hollow cylinders, cylindrical shells. I actually hate the name shell method. I feel like cylinder method would make more sense. Shells isn't very informative to me. Doesn't give me an image. But anyway, it's a shell method, so everyone calls it that. I'm not going to rebel yet. Once I have my $5,000 textbook I publish, maybe I'll try to make some waves. I actually would like to make my own textbook, but it wouldn't be $5,000. Okay. Find the volume. If I want to get rich, I'm not going to get rich from my students. There are better ways of getting rich, I think. Better people to take advantage. Find the volume of the solid of revolution. I want to keep my job. Formed by revolving. I don't think I have to cut that out of the video. If you have a complaint about anything in the video, please let me know and I will do my best to apologize. Formed by revolving R about the x-axis. I have completely lost my train of thought. It wasn't even that bad. R is the region. Should just stop talking about it. Bounded on the right by the function g of y equals 2 square root of y. Bounded on the left by the y-axis. And y is in the interval from 0 to 4. So lots going on here. These problems are so wordy. As these videos go on, I'm gonna abbreviate this like more and more. But I'm trying to be at least a little precise for y'all. Okay, so square root function. Square root function normally looks like this. But it's a square root function in terms of y. So think about it like this instead. Kind of the sideways of a parabola. This is g of y. Root y. So this is bounding our region on the right. And on the left, it's the y-axis. And we're just looking from 0 to 4. So again, if this is 4, our region then is just the region between these from 0 to 4. Again, we could set this up with the disk method. Oh, and we're revolving it about the x-axis. I want to show both setups on this one, and let's do it on the next page. I have more room. So with the shell method, again, it's pretty quick. Shell method, we need these little shells. And we just take all these rectangles. Height of the rectangle is the function value. Again, the y coordinate, the input is the y coordinate, the output is the x coordinate here because it's a function in terms of y. Should really draw this picture more. It's, I think, very important and helpful. So the shell method says, yeah, we just add up all those volumes from what happens when you make a little shell out of this. Sorry, when you make a little shell out of this. This way is the shell, right? Well, that's going to be just volume is 2 pi integral y. Again, we're rotating about the x-axis. So the shell method says that everything should be in terms of y. Y is going from 0 up to 4. Y times g of y, which is 2 root y. And that's no problem. What does the other method look like? The disk method. Well, the disk method would have us make circles out of these rectangles. Oh, so it would technically be the washer method, but it's pretty much the same. This is the point 2, 4. So if we use the disk or the washer method, I hate that it has two names. It's basically the same thing. We get it's pi times the radius squared. X is going from 2 to 4. From 0 to 2. And the top function is just a constant function, 4. So it's top function squared minus the bottom function, which we'd have to find. Right? If x is equal to 2 root y, that means 1/2 x equals root y, or y equals 1/4 x squared. We'd subtract 1/4 x squared with respect to x. So again, both of these methods work. And the second one's not even awful, but it just takes a little bit more work. Disk and washer method, both A-OK here. But we're just, sorry, shell and washer method, both good. We're just going to only do the shell here. But you could do this out and you should get the same answer. That would be good practice. So we're going to get 2 pi. We don't want to integrate this yet. We have a product. Products inside of integrals are usually bad. We need a u substitution. The only thing that we could see on the inside would be y. But if this is not a substitution, this is just a change of variable, which is another way of saying substitution. But this changes nothing. Just changes the letter. So don't do that. We're just going to combine terms. Because this is y to the 1/2. So we're just going to get 2. Well, the 2 can come out in front, right? 2 is a constant. We can factor out constants. We cannot factor anything else. Only constants can come out in front of the integral. This is y to the 1st times y to the 1/2. That should be y to the 3/2. So 4 pi. Now we can antiderivative. Add a power, divide by the power. Plug in 0 and 4. 4 pi times 2/5. We could have taken the 2/5 out as well. This is the square root of 4 to the 5th power. Square root of 4, raise it to the 5th power. Square root of 4 is 2. 2 to the 5th power is 32. Plug in 0, you get 0. So we get 4 pi times, this becomes 64 over 5. Hopefully. And when you multiply this all out, 256 pi over 5 units cubed. Now, let's check our answer in two ways. Let's see if the washer method gives the same result. Let's check with Desmos. And we see that our shell method is correct and our washer method is not. So again, just shows that sometimes the easier one is, well, it's easier. And that's because I have the wrong x coordinate up here. I did the x coordinate if it were square root of y, but it's not. If y is 4, what's our x value? 2 times the square root of 4. This is actually 4 comma 4 up here. And if we replace this up here with a 4, we should now get the correct answer with the washer method. Now the washer method agrees with the shell method. Okay? So again, you can use both, but again, this integral is harder to set up and harder to evaluate. Case in point, me messing it up. All right, so that is the end of this video. Next video, we're gonna see what happens if I don't revolve around the y-axis anymore, or the x-axis anymore. What if I want to revolve it around some other line? Okay, stay tuned. Good luck. Bye-bye.